So why are some amino acids glucogenic and some ketogenic? Like, why can leucine and lysine not become glucose?
Why can't leucine and lysine become glucose?
Yeah. Because everything else is ketogenic or is glucogenic somewhere along the way, right? Leucine right here, and lysine right here. Those are the only ones that are never glucogenic anywhere.
Huh. Right.
Because you see like phenylalanine comes in over here, right? Tryptophan
Right.
comes in over there somewhere up here, right? So all of those things come in at least one spot where they can be glucogenic, but except leucine and lysine never do.
I'm not sure why. Or why specifically.
So the reason it has everything to do, well, notice where things are. So yellow in this picture, yellow in this picture is ketogenic. Pink in this picture is glucogenic, right? So notice that all of the yellow is in 2 entry places and everything else is pink.
Right.
With this picture. Okay. So the reason is the trend here that if you enter the citric acid cycle as acetyl-CoA, and here we're tracking carbons specifically. So the carbons that come into the citric acid cycle as acetyl-CoA never can be incorporated into glucose because they go away before glucose gets made. Specifically, they become carbon dioxide before glucose gets made.
Okay.
Yeah. So if we scroll back up briefly to the citric acid cycle, you can see that when acetyl-CoA comes into the citric acid cycle, it turns into citrate. Citrate is 6 carbons, right?
Right.
Citrate, 6 carbons. Citrate gets turned into isocitrate, also 6 carbons. And then isocitrate gets turned into alpha-ketoglutarate. Alpha-ketoglutarate is only 5 carbons.
Okay.
Right, because we're getting rid of a CO2.
We're losing a carbon. And then the same thing happens for coenzyme A.
Yeah, and so here we're at 4 carbons, right? And so these 2 carbons that leave are the 2 that came in as acetyl-CoA.
Right.
And so that's why those can never contribute to the formation of glucose, because they only enter the citric acid cycle as acetyl-CoA. And so they get respired off before we ever make it around to oxaloacetate, which is the thing that can go become glucose if it wants.
Okay.
Yeah, so that's like the main thing underlying the glucogenic versus ketogenic amino acid situation.
Okay.
So
and can you scroll back down to that other image?
Oh yeah, for sure. Yeah, let me zoom out just a little bit.
So then those, right, for the ketogenic ones, it makes sense because they would have to start at acetyl-CoA and then be entered into the citric acid cycle. But then how is it that the glucogenic amino acids can enter in like the middle of the cycle? Why don't they all just start at pyruvate?
Why? Oh, you mean like why don't all of the amino acids just start at pyruvate, or?
No, like, so there's like 4 places in the middle of the cycle that they can enter.
Yeah.
By they, I mean the glucogenic ones. But then a bunch of them can also enter from pyruvate. And in my mind, it makes sense that they would start at like the beginning of the cycle. So how is it that some of them just enter in the middle?
Yeah, it's because the cycle doesn't have a beginning in real life. Like, it's just the way that you've been taught it over years.
Right.
And yeah.
Right.
So they just come in wherever their structures match up with the thing that is the citric acid cycle intermediate at that point. And so it just depends on what reactions they've undergone. For instance, the glutamate to alpha-ketoglutarate one is the one that's probably the highest yield here. So here's that. So you've got this glutamate dehydrogenase enzyme that takes glutamate and turns it into alpha-ketoglutarate and vice versa. Right? You can also take, if you have too much alpha-ketoglutarate build up, this enzyme will push the other direction, incorporate ammonium, and then become glutamate. If, for instance, you're in an anabolic process where you're wanting to build up a bunch of, I don't know, muscle or whatever else, any other protein.
Right. So right, that I think it's because I'm thinking about this so linearly that I'm
Yeah,
confused.
I think
But
so too.
yeah, but so I understand that glutamate can be made into alpha ketoglutarate.
Mhm.
Is it that in the process of moving from citrate to alpha ketoglutarate, or right, because there's citrate to isocitrate and isocitrate to alpha ketoglutarate, right? So then if it's entering at a point where instead of isocitrate, it's it is forming alpha ketoglutarate and the cycle continues at the same time where like some isocitrate is also doing that.
Yeah, yeah. So you're saying like if one of them comes in as acetyl-CoA or whatever, and then turns into citrate, then isocitrate, can that be happening while a different one came in as alpha ketoglutarate, and then be
Or
happening at the
as
same time?
glutamate turning into alpha ketoglutarate. Like is that it's not like it what I guess what I'm asking because to clarify that this isn't linear.
Mhm. Yeah,
It's
yeah,
not that like glutamate suddenly replaces and isocitrate is out of the cycle now, but
r-
rather it enters and forms more alpha ketoglutarate at the same time as maybe isocitrate has already been made and is going through
yeah,
that same
yeah.
process.
Oh yeah,
Okay.
for sure. Because every mitochondrion that you have is gonna have like millions of isocitrate dehydrogenases all making isocitrate at the same time, or making alpha ketoglutarate at the same time. So like every single one of these things
Oh.
is happening like billions
Okay.
of times all at the same time.
That is so sick, but I hate that so much. My mentality is like, you know, like the mitochondrion is the powerhouse of the cell, meaning there is one, we have one.
Yeah.
Things happen orderly.
And
Things are not happening orderly.
maybe that was true at some point in time, but then
Right.
one mitochondrion in one cell somewhere found out that if it's made two of each enzyme, then it would beat the others. And so then all of them started doing that. And then, and then
Oh my god. Suddenly this makes sense. It doesn't just like wow, okay. That seems so logical, but like this is genuinely the way I've been thinking about metabolism, which is why it's like impossible to memorize or understand rather. But like things aren't being replaced, things just don't stop.
correct.
This is just supplementing
Y
essentially.
Yeah, yeah, exactly, and so then there's this situation where you've got, like so now because also that you have a reaction where, so you've got, like, isocitrate plus some stuff, right? Isocitrate plus, we'll just say, like, NAD plus is at equilibrium with alpha that's not an alpha, with alpha ketoglutarate. I'll just write alpha keto, okay? Alpha keto G, how about that? Alpha keto G plus NADH plus CO2.
Mhm.
So that's a reaction that sets at equilibrium. And so now if we get like a whole bunch of glutamate coming in here turning into this, then
Uh-huh.
like maybe we're in a state where we're eating the carnivore diet. And so we just have a shitload of amino acids that we're pulling in, right? So
Uh-huh.
rather than just like have all those amino acids sitting there, we're going to take some of them and turn them into alpha ketoglutarate. Well, that's going to increase our levels of alpha ketoglutarate. So this equilibrium is going to shift this direction across that entire mitochondrion. And that doesn't mean that we're going to take all this alpha ketoglutarate and turn it back into isocitrate. That's not really what's going to happen. It's just that we're going to now slow our production of alpha ketoglutarate. Therefore, levels of isocitrate are going to increase a little bit.
I see. And like that process shows alpha ketoglutarate can also become glutamate if there's like too much of it, for
Oh yeah,
example,
for
and you
sure.
just make amino acids instead.
Yeah, yeah. If we're on the Snickers diet and not eating any protein at all, just tons and tons of carbs, then you're
Uh-huh.
going to break down glucose, right, to pyruvate and then turn that into acetyl-CoA.
Uh-huh.
Combine that with some oxaloacetate, make it into citrate, make it into isocitrate, and then all of a sudden make that into alpha ketoglutarate. And now we have this is at equilibrium as well. The glutamate to alpha ketoglutarate situation, that's also an equilibrium. And so since we have really, really low glutamate, our equilibrium is shifted hard upward here toward glutamate. So you've got alpha ketoglutarate getting shunted into glutamate so that you can still make proteins and stay alive, even though you're being an idiot and just eating Snickers.
Oh my God. Okay. Wow. Everything just made sense. That's
See what I'm
awesome.
saying? Yeah. So that's what I'm saying. Like
Okay.
everything really is going to come together in this last month as you
That's
head downhill toward this test.
horrifying.
Isn't it? It feels good though. Like
Everything.
it's really exciting.
Yeah. It's overwhelming, honestly. Everything is happening all at once all the time. I'm like shocked my body is alive. Truly.
Yeah. No kidding. Yeah.
Yeah.
Yeah. Well, the first iteration of you was one cell because this is a lot to keep track of, and then you got better at that.
True.
Yeah.
Wow. The more you know.
Yeah. And then as you got more and more resources and it became easier because of specialization, you decided to throw a neocortex on top so you could consider all of it.
True.
Yeah.
And then it got complicated.
Yeah. And then it got worse. I'm just kidding.
Regrets.
Yeah. Then
Wow.
neocortex figured out how to make everything harder for everybody else.
Whoa. Oh, that's so cool. I hate it. Okay.
Yeah. Yeah, so that's what I'm saying, that the end of this process, I think, is really fulfilling because you get to see how all the pieces start to connect together, and it really gives you, I don't know, like some hope for why you're learning all this, that you actually feel like you're coming out of the other end of college and prep for med school
Yeah.
with as a
Wow.
person who knows a lot of stuff.
I needed that.